ओके, सो अभी हम स्टार्ट करेंगे मोशन ऑफ सेंटर ऑफ मास। इसमें इस आर्टिकल में हम पहले तो सॉल्व करेंगे कैसे जो है इसका रिज़ल्ट आएगा, फिर उसके बाद हम कुछ एग्जाम्पल्स की हेल्प से इसको अंडरस्टैंड करेंगे कि फिज़िकल वर्ल्ड में इसका क्या इम्पोर्टेंस है। सो लेट्स कंसिडर अ सिस्टम ऑफ एन पार्टिकल्स। एन नंबर ऑफ पार्टिकल्स हैं, मासेस उनके दे रखे हैं M1 M2 M3 से लेके Mn तक, और R1 R2 R3 इनके जो हैं वो पोजीशन वेक्टर्स हैं रिस्पेक्टिवली। देयरफॉर सेंटर ऑफ मास ऑफ सिस्टम हमें पता है क्या होता है, M1 R1 प्लस M2 R2 वेक्टर प्लस सो ऑन Mn Rn वेक्टर डिवाइडेड बाय सभी मासेस का सम M1 प्लस M2 प्लस ऑन Mn तक। ना इसे हम ऐसे भी लिख सकते हैं कि जो आपका M1 प्लस M2 प्लस M3 है, ये सभी मासेस का सम, पूरे सिस्टम के मास जितने भी पार्टिकल्स है पूरे सिस्टम में, उनका सबका अगर हम सम करें सो वो पूरा जो सिस्टम है उसका मास हम मान लेते हैं कैपिटल M में। ये रहा हमारा मास ऑफ सिस्टम। नाउ लेट्स सी, सो दिस ओवरऑल विल बी कैपिटल M. So we can write it as capital M RCM, position vector of the center of mass multiplied by its total center of mass of the system will be equal to M1 R1 plus M2 R2 vector plus so on Mn Rn. Okay, हाँ, अब हम क्या करेंगे, let's differentiate both sides with respect to t. Differentiate both sides with respect to time. So we can write mass is constant, so m will be out and it will be d over dt RCM is equal to, same here, m1 will be out of the box and mr1 plus dr1 by dt plus m2 dr2 by dt so on mn drn by dt. So we know that change in position, this is position vector, so change in position with the time is actually the velocity. So we will write it as, all these things will become the velocities. So let me erase it. I will erase it whole. So we have m v RCM, or we can say VCM, velocity of the center of mass. So velocity of the center of mass multiplied by mass of the system will be equal to m1 v1 plus m2 v2 plus m3 v3 so on mn Rn, sorry, Vn. It will be mn Vn. No, velocity of the center of mass is VCM here. This is the velocity of the center of mass. Let's say this equation as first equation, and v1 v2 v3 are the respective velocities of m1 m2 m3 and so on. And now let's differentiate it again. Differentiate equation 1 again with respect to time. Now we will see that it will be m dvcm. I will write capital V for the velocity of the center of mass, by dt will be equal to m1 d over dt v1 plus m2 d by dt v2 plus so on mn d over dt vn. Now we already know what is dv over dt. Yes, it is acceleration. So m, acceleration of the center of mass, will be equal to m1 a1 plus m2 a2 plus so on mn an. Always when you're doing calculations, doing articles, derivations like this, always give the reason in your answer. Like dv by dt is actually, we know generally it is the acceleration, so that's why we were able to write dv1 of d as a1 and so on. Now we have to use the second law of motion. We already know that in using the second law of motion, Newton's second law of motion, we know what F will be force is equal to mass times acceleration. So MAC, center of mass, acceleration of center of mass, will be equal to M1A1 will be equal to F1, force acting on the first M1 particle. So it will be F1 plus F2 plus F3 plus F and so on, Fn. Let's say this is the equation number 2. Now these are actually the F1, F2, F3 are what? They are actually the external forces acting on it. Like individually on particles, the external forces which are acting. Let's say there is a force acting on the particles. So F1 is the force, external force acting on the particle M1, and F2 is the external force acting on the particle M2, so on. So external forces on M1, M2, Mn respectively. So equation 2, how we can write the equation 2 then? We can write equation 2 as, like, if you add all the external forces acting on the individual particles, if you add all the forces, that will be equal to the total external force. So MACM will be equal to F external, total external force. So here we can see that, like, the if you see all the particles separately and take it as a system, so whatever the center of mass will be, if you consider that point and see that if F external is working on it, they are the same thing. So center of mass of a particle system moves as if whole mass of the system were concentrated at the position of the center of mass and all the external forces were applied at the center of mass. F1, F2, Fn are working in such a way that as if F external, one force F external was working on the point of the center of mass. So this is how we explain the motion of a center of mass. Now let's understand it with more detail with few of the examples. Okay, so now we will study about the center of mass motion and some examples of it. First example is a very interesting example. Okay, so the first example is the motion of Earth around the Sun, that is elliptical. We know that the motion of Earth around the Sun is elliptical, simple as that. And we know that Moon also revolves around the Earth, but Earth's motion around the Sun is elliptical. On the other hand, motion of the Moon around the Earth is circular. That is the circular part. This is the difference. So both the Earth and the Moon move in circles. And interestingly, let's say this is the center of mass, and the way actually Earth and Moon revolve around each other are in such a way that they are actually revolving around the center of mass. It's not that Earth is just revolving only here, but there is a motion here as well, a little bit of it, negligible. We have zoomed this portion here. Actually, as compared to the Sun, Earth is only just a point, so I have zoomed it to make it understandable. So the Moon revolves around the Earth in a circular path. However, Moon actually revolves around the center of mass of the Earth and Moon system of particles. So let's say these are the system where we have two particles, Moon and the Earth. When they revolve around each other, they move in such a way that there is a center of mass in the middle and they revolve around that center of mass. Earth and moon are always on the opposite side of the center of mass. Here is the moon and here is the earth. Remember, it's very important that moon and earth are always on the opposite sides of center of mass. Whatever the center of mass of both these bodies is, they seem to be opposite in direction to each other. Now we will see that the earth is quite closer to as compared to the center of mass as compared to the moon. Why is that? It can be simply explained as the earth is heavier than the moon. Earth's mass is heavier than the moon. That's why the center of mass of the system is very close to the earth to make the balance. It's a balancing point. So it will be a center of mass will be much closer to the earth as compared to the moon. So this is an example of the center of mass motion. So this is first example. Now let's move on to the explosion of projectile example. This is also an example of the motion of center of mass. So let's understand it in more detail. What happens is, once let's say it's in the midair. So you throw a cracker in the midair and it will explode at one point. But firstly you have it is like a projectile. It's not yet blown. So we consider a projectile which explodes in the air. So before explosion, let's see what happens. The projectile moves the parabolic path. This is the parabolic path of the projectile. Simply when you have lighted the cracker and then you throw it, it will be simply following the parabolic path. This will be the parabolic path followed by the cracker itself. But what's different here is that cracker will explode eventually in the midair. So it will have many different particles. So when it explodes, let's say the particles are M1, M2, M3, M4. These are the particles which all when added up makes the particle M, cracker's mass M, and which is equal to M1 plus M2 plus M3 plus M4. So what happens is the mass of the projectile. So the projectile itself will keep on moving this way, but the cracker's particles M1, M2, M3, they will have their own parabolic path now. They will move their own parabolic path. So let's explain why this happens and how this happens. So the projectile follows a parabolic path under the action of gravity. So projectile is going on, projectile is there, main projectile cracker, but it is under the gravity. What happens is there is an external force, gravity here, gravity, Earth's gravitational force. So explosion, but the explosion of the projectile, the explosion which is happening is only because of the internal forces of the cracker. Let's say there are some dynamite or we can say a chemical reaction going on inside the cracker. That is the internal forces. So the explosion itself, it happens because of internal forces. So when there are internal forces, these internal forces cannot change the total momentum of the system, or in other words, they will have their own parabolic path which cannot be changed. But while they are on their own parabolic path, all the masses will still be following a path, main path, parabolic. As you can see, when they will reach here, they will still be falling like this, but they will be falling according to this path, main path here. So this will be the path of the center of mass of the cracker projectile. So these internal forces cannot change the total momentum of the system, although they may change the momentum of the individual fragments. So individually fragments have their own momentum that may change, but the overall, the center of mass will remain unaffected by the explosion. So it will keep following the same projectile path. This is the another example of the center of mass motion. Let me give you one more example. Let's take one more example, last example. um, okay, let's say there are two binary stars in the universe. There are many types of stars. There are different stages, and the way they interact with each other, we can say there are different types of stars in the universe. Let's take an example of the binary star system. Binary star system is such that there are only two stars which are kind of revolving around each other, because they are in vicinity of each other. They are attracted to each other because of the gravity, but they may get affected by the other terrestrial objects as well, like other planets or other suns. So in the universe, let's say the Sirius is a example of a binary star system. It's a binary star system. We are saying it as a system just like the system of particles. If we have two particles, or we can say we have two stars here. So in this case, one member of the pair is Sirius A. Let's say yes, this is the path being followed. This is the path being followed by the Sirius A. Let me write A here with the mass MA, and this is the path of the Sirius B, MB. Okay, so these two are the paths of both the stars. This is the Sirius A, this is the Sirius B's path. See, they're not like revolving around each other. They are following an elliptical path. They are not actually revolving around each other, but revolving around a common path, a common center. That's the interesting part here. That's what makes it a center of mass motion, because they're actually revolving around a center of mass. Let me draw it a little. Let's see. It's a axial line here, center of axis, and there is the center of mass. They both seem to be revolving around the center of mass, just like Earth and Moon. And Sirius A, which is a brighter star, it's a bright star, and other member Sirius B, it's a faint star, let's say. Yeah, so it's brighter one and it's a faint one. It's a faint star. Now the two stars move in their own elliptical orbits around the common center of mass, as we are showing in this figure. According to the definition of center of mass, let's say according to the definition of center of mass, what's the formula? Center of mass, position vector for the center of mass of these two stars will be MA, Sirius A, R. Let's say this is the position vector from the center of R1, or yes, R1, and let's take this as R2, R1 and R2. So MAR1 vector plus MBR2 vector divided by MA plus MB. So this is the center of mass, and so since the center of mass coincide with the point, let's say we assume that they are revolving around a common point, and we made the center of mass there as well. So if they are coinciding, like if this is the origin of the xy axis and center of mass is there only, we have made the coordinates in such a way, we have drawn the diagram in such a way that this is the 0, 0 point, right? This is the 0, 0 point, or the origin point. According to that, then it means that simply RCM, position vector of the center of mass itself, will be 0. It will be 0 if it is the origin. 0, comma 0. Now it will be this, and 0 will be equal to this hole here, and this we can ignore it. It will go there, and this can't be 0, right? This can't be, denominator can't be 0, but RCM is 0. That means this itself, this value only is 0. So MAR1 plus MBR2 vector will be equal to 0. Now what becomes of this equation? Let's see. So MAR1 vector will be equal to minus MBR2 vector. Now MA divided by MB will be equal to minus R2 divided by R1. So this is the ratio. So the two stars exert equal and opposite internal gravitational forces on each other. They are applying forces on each other, equal and opposite, and hence their net external force will be 0. But in reality, what happens is, other maybe there is a very let's say there is a black hole nearby. So that its own gravitational force will be very high. So these motions will be affected by other celestial bodies as well. So it's not always exactly like this, but ideally, if external gravity is not working on them, then this will be the case. We can study it in this way. Okay. Now, lastly, but not the least, very important, some of the conclusions is that, first, very important, about the position of the center of masses. Okay. So this was the rotatory motion. This was the kind of rotation. So rotatory motion. We studied translatory motion, right? Let me see if we can go to that slide. We have to jump to there. Okay, so there were two kind of motions, rotatory motion, and the first one was translatory motion, which was every particle was moving in the linear way and with equal velocities. But in the position of the center mass for rotatory motion, the position of the center of mass, let's say this is the rotatory motion of the system of particles. The position of center of mass remains unchanged. It remains at the same times. Both MA and MB are moving. They are moving. Center of mass is there only. It is not moving. So it will be remaining unchanged. Its position will be same always in the rotatory motion. But in the translatory motion, in the system of particles where there is translatory motion, at that kind of system, the center of mass position will be changing. Always. It will be changing with time because the whole system is moving. And center of mass itself, remember that it remains at the same point. For the rotatory motion, it remains at the same point. So wherever you start your coordinate system, if you want to study by taking the x coordinates and y coordinates and want to go for the position vectors, it doesn't matter where you take your coordinate system, the center of mass will remain at the same time. It is independent of the coordinate system that you take. That's the last important point I want to tell. That's it. Okay.